Swayam Prabha. Digital India. Educated India.
Okay, so that's the next topic is going to be P large delta amplification. But what I want us to do, I want to get you in a good place with consteel, and I'd like to do it by basically implementing a model of a frame that essentially an L frame that we were just studying with particular dimensions. And then Lakshmi and I are going to talk about plugging the results from those analyses into some design calculations by AISC 360 and by the Indian standard to kind of wrap up the discussion today. And so, so we're pretty much on till 4:15 for the second module. So I think we should go ahead and look at moving into that. So has everybody had a chance to load consteel? And you may have already tried to experiment with it some. But so what I want to do is, and you've got a handout here. I think so everyone has the handouts. The handout that basically says if you have consteel 17 loaded, so let's just type consteel to get started. And so the idea here is we'll kind of step through this together. Okay, so this is the starting menu that comes up. So we'll just give this a name here for our model. So I'll call it L-frame for L-frame demo. And one of consteel's strengths is basically implementing Eurocode. I think that's their primary clients or engineers using Eurocode. They've implemented a version of AISC 360, so we're going to work from that. Balant was excited yesterday, but he said, "Look, I'm looking at all these things in the Indian code, and the column design, the beam design, we've already got all that. That's Eurocode." Okay, and we can give it a little description, and then create. All right. All right, so we're on step 3, I believe, of the handout here. And so if you use your mouse wheel, you can zoom in, your center mouse wheel, you can zoom in and zoom out. Everybody good there? If you simply push down your middle mouse button, I said click with your left mouse button, but here I'm actually pushing down my middle button and dragging, and I can move the display around. Okay, everybody good there? All right, so mouse wheel zooms in and out. If I hold down the mouse wheel and move my cursor, I can move whatever it is I want to move within the display. And then I think this will show up, and I think I probably have it shown up in several places. If you push Alt key button, and click and push the left mouse button, you can rotate into any position you want there on the display. Everybody good? We can see how that's working. So I've got my finger on the Alt key in my display, and I'm holding down my left mouse button and dragging my cursor around. We're good? All right, now the first major step, if we're defining a frame, is to select our structural member cross sections. So you can see there's the broad menu at the very top, and then menu bars. Right now, this is the third level of menus are for geometry. If I click structural members, now the third level corresponds to structural members. And you can see the structural members mouse button or tab there is bolded now, right? So we're in structural members. And then if you go to the leftmost button in the third row, that's section administration. So if you left click on that, you get this window that shows up. We're good. And then we're going to go from library. So we're going to just pull a section from, a rolled section from the libraries in Consteel. And you can see they're different national clients here. We're going to use American. I don't know when the Americans are going to finally, we tried to convert over to SI system like 15 years ago, and that didn't go very well. We're back to US or imperial units, and it's very painful. So, okay, yeah, sure, I'd love to come and talk to you guys, but I really don't want to lecture to you in imperial units. So let's convert everything to SI. And in Consteel, we're going to work mostly in SI, but they have some aspects to help to accommodate engineers that are more familiar with the US or imperial units. So we're going to look at American. American is SI units. You don't want to go to American Imperial. And then H profiles will allow us to look up wide flange sections. And so if you click on the W here under H profiles, you can bring up the library of wide flange sections that are available in Consteel. I think these are most of the ASTM sections that we're using. Right? UB? Universal beam? Yeah, so we're using the ASTM profiles here, but actually I think if we go to your code would have universal beam sections too, right? Europe, Australia, but different ones. Right, okay. Okay. Oh, okay, good. All right, now the particular section here that I want to use is a 200 by 59. So I'm going to find that one here. So there. So I can click on that, and then we'll load that section into Consteel. So actually, so now Blint pointed out to me, because I showed him what I had prepared for you guys, and he basically pointed out, hey Don, you could have changed the material here under this menu. So I've got it, the European material. If I close out of this, if I come back to the section administration window, and we can edit. So if I click on this one section that we've chosen here in the table, and if I go to modify, I can now come down to section material and click on that menu that we could have done earlier. And I'll scroll down, and in American practice, ASTM A992 is very common. So I'm going to pick that. I discussed this with Lakshmi earlier, particularly so Balan has all these different, I think he doesn't have the Indian sections here though, but other programs that we'll look at a little bit, we'll look at another program called Mastan some, and Mastan has all the ASTM profiles in SI, but has little of any other. So I could do American profiles SI very easy, but some of the other ones not so easy, right? Okay, so I've picked that, so now I modify so that I've now changed the material. Actually, if we go back also there, oops, that's not what I wanted. Let me go back to the section administration window again. Pick this and modify. If you click on the button that's the ... out to the side, you'll see that in many places, and that allows you a window into, let's actually explore what's available with the different steels. So, for example, I could go coated steel and say, okay, what are they using for the A992 grade 50? Oh, okay. So elastic modulus, 200 gigapascals, FY 345, so basically 50 KSI, etc. In some of the cases, I think it may be because of more of the cold formed area, you'll see the modulus of 210 gigapascals rather than 200. 200 is more the common practice for these in ASC 360. Would that be also the case in the Indian standard? The material's pretty much 200 gigapascals? Okay. All right, so we've got our column section, that the section we're going to use for both the column and the beam here. So we can close out of this dialog window, all right? And so now, if we look at the other buttons that are available in the third row, this one, it allows us to put a column in. So let's click on that. Now what you're going to find there, we'll be able to illustrate it better with some other cases later. This is a fairly small frame here. Consteel works entirely on, let's draw all the members. Let's get all the members in. We're never explicitly saying, here are the nodes. We're not generating nodes. Consteel handles all the finite element nodes under the hood. So I basically say, I have a girder that goes 200 feet. I've got various members connecting into that girder. I draw the whole girder. I draw these other members. Consteel recognizes, these come into the same point. I'm going to put a node there. So I never have to actually explicitly define that node. So hopefully that kind of gives you that feature of pretty much drawing members. Everything's member-based. And then the connectivity, you can control that, but it's very efficient in terms of being able to create your models by having that scheme for doing things. So here we're going to create a column, and so we're going to do this L frame, and the column is going to be 7.5 meters tall, and the beam's going to be 7.5 meters long. And so we're going to work in millimeters units, and so we'll go ahead and put in the 7,500. Okay, it's the 200 by 59 section. That's the only one we picked here, so that's showing that. Generally, it'll show whatever's the last one you were working on in the section administrator. Start and end point, we'll make those continuous. This basically gives me an option where I can put in releases if I want in the model at the member ends. We can put in bow imperfections if we want. We won't go there right now. That may show, we'll probably look at that a little bit with some bracing, stability bracing considerations later. And number of finite elements, Consteel kind of has it sorted out. Typically, it will provide 6 elements for every unbraced length. I think it doesn't always work out exactly to that, but that's kind of roughly what you usually get. And I'll show you later that that's actually a good recommendation if you're doing analysis where you need to consider anything that's torsional behavior or lateral torsional buckling. For the type of element Consteel is using, which it's what we call a cubic Hermitian type finite element based on cubic displacement field. 6 elements per unbraced length gets you about what you need to have accurate results for lateral torsional buckling, etc. Here we're going to explore.
So what do they mean by 7 degree of freedom beam element?
Okay, so every node has 3 displacements, 3 rotations, and then what we call a warping degree of freedom.
How do you define the warping?
Yeah, so the warping, if it's an I section, it's simplest. So warping is simply a cross bending of the flanges. So warping is when the flanges are bending in opposite directions. So you can add that to the lateral bending of the flanges. So, say it again.
The release point,
Mm-hmm.
I saw something called W. If you drop down the continuous thing,
Okay.
it's an XX, Y, Y.
Okay. Now that's that we're getting into releases. Let's say you want to put in a model that's a perfect spherical joint, bearing joint, and so then you would release XX, YY, ZZ, and so now it's free rotation there.
There's also something called W there.
W means you're also releasing the warping. Okay, and so here, rather than take the automatic, I want us to look at it first with just 4 elements per member. So we're going to just set that as 4. Okay. So now we're in a good place where we can place our column. And so what we want to do is to come in and kind of hover. We're going to put it at the column at the origin. So kind of hover there, make sure and it will snap to the origin when you click. So click on that. Okay, so and now I've got a column. Okay, and that's our only column in this problem. So we can close our window here. So now let's go ahead and do the beam. And I'm going to actually do one thing here. I'm going to kind of set my orientation. Okay. All right, so for the beam is actually general. If it's a column, basically it's going to give you a member that's oriented in the Z direction. If you look at the coordinate axes, they're shown in the lower left of the screen. So a column is by default Z. A beam could be any direction. Okay, it doesn't have to be horizontal. So we're going to insert a beam. Again, the only section that we've picked right now is the W200 by 59. We're going to basically assume we've got full continuity with the column at the top, but we'll set it for 4 elements in the beam. So for the beam, it wants us to do a start and an end point, and so any point we've already selected, if we wanted to put it into the middle of the beam, it has some control points. The column, you have some control points along the column you can see highlighted there. That's related to the N over here in the lower right, N of 4. Here, I could set that to something else and I would see more points that are points I could snap through along the column length to insert things. I want to basically put the beam at the top of the column here. And so if we click at the top of the column, and so now you drag your cursor without holding any of the keys, and so just let go of your mouse. Don't touch your mouse. You got it out there, and then type X at your keyboard. Okay. And so notice down at the bottom of the screen, it's now in blue. It's highlighted X. Okay. And now also notice that there's the orange triangle at the bottom. That's telling us that we're actually in a relative coordinates. So it's going to go, any number I put in is going to be relative to the start point. Whereas if I clicked on the little globe, I can say, oh, I want to just put in a global value and go to that specific XYZ. Okay? So relative, I want my beam to be 7.5 meters long. So under X, I'm going to do 7500. Okay? All right, and then I don't want to go any dimension in the y. Y is 0, z is 0. So you hit y. Notice it highlights the y value now. Put in 0. And then z, put in 0. Return. Okay? That takes a little bit of getting used to it first. I don't know how, if you keep your hand on your mouse.
Is there a control Z?
If you put it in wrong, you can you can go to edit and undo. Okay, or you can also just select the member. I get it to select. Oh, okay, yeah, it's here. Okay. And I can. So how do you delete a member? You hit no. I'm posing it as a hypothetical. If you need to delete something on the screen, yeah, that's good. You can undo, or I think I actually just ended up accidentally inserting some extra beams. So I'm going to fix that. If I need to delete something, well, you've got your delete key on the keyboard.
So you just select and delete.
Yeah, right. Just select it and delete. Okay. No, it looks like I was actually okay, I believe. I'm going to come back and is that thing out there? Okay, I want to double check. Yeah, I think that's okay. All right. So actually, given what I just did, I could redo, and I think it'll put it back. Nope. Okay. Let me do it in my beam. So if I come here, okay, so I select the top of the column, I drag my mouse button out, let go of the mouse. If you've got your hand on your mouse, it'll screw up your X, Y, Z. X, 7500, Y, 0, Z, oops, X, 7500, I hit X accidentally, Z, 0. Return. Okay? All right, so we got our beam and our column. Never defined any nodes. All right, now, at this point, this is probably a good place where we can explore different views. So this is the view that's automatic here is a wireframe view. So you're just seeing the edges of the members. If we go to the hidden line view, you get this, and your screen may look a little bit better than mine. I didn't try to fix it because being on the road, I wanted to be close to my IT guys if I was going to start messing with my video driver. But Balint was telling me that he thinks I need to probably install an update to my video driver. I'm getting kind of some extra lines there in the hidden line view that are a little bit ugly. Hopefully yours maybe looks better than this.
Where do you have the options for rendered view?
So that's over here. So this is the wireframe view, and so this is the hidden line view. So you see a dark line representing each edge. This is a solid view, okay? And then it's often very helpful when we're building a model to go to just a line view. So then you can click on the reference axis of the member more easily, okay? So those are all useful options in different contexts for doing things here. And so that's basically explained in I think the items 14 and 15 of the handout.
How do you take care of the connection?
The connection is automatic
So it assumes a rigid connection.
unless we put in a release. Okay. So there's a few very interesting features of Consteel here that we're going to implement here with this small model. So one is you can, if you do that by default, it assumes that everything is rigidly connected. Now we still have, when it comes to warping, okay, warping in the beam at the knee joint is not the same as warping in the column. Some very sophisticated aspects there that only a few people, Nick Traher in Australia and a number of others have explored over the years, and they've implemented it. Basically, model for different types of details at the joint, how does the warping continuity transfer through the joint? It's basically a thin-walled open section beam approximation of what you could get if you actually ran a shell finite element analysis at the knee. Okay.
How critical is the warping degree of freedom in these calculations?
Warping is essential when it comes to stability of thin-walled open sections.
Because we don't account for it. In the discussions we have had, we have not included.
We'll get there. So most of the things we've talked about so far are planar solutions, but we're going to touch on some aspects with this that relate to, I've got a frame that's loaded in the plane, but it can fail by lateral torsional buckling. And so we're going to explore that quite a bit. Okay? Everybody in a good place with this one? So now, I think 16 basically says, okay, well, if you hold the Alt key down, you can rotate your structure around and look at what you've got. Again, hold your middle mouse button down. You can drag it. If you spin your mouse wheel on the middle, you can zoom in and zoom out. All right, so we've got a frame. We need supports, obviously, for a frame. And so we're going to again, everything is member based. So supports supports for the different members. And yeah. Oh, the orientation. There was I think. Let's look at the column menu. Good question. I think the orientation is the degree here on the local eccentricity. There's that, and then also I think that question I can tell you for sure. Again, for things the real pro will be here next week, but I can tell you things I've learned quite up to a point. So if we look at let me explain what's over here on the right. I think I'm going to say something about that in the handout here shortly. But if you look at view, it's basically the object properties. And so let me right click in the main window. It's a little bit confusing. It doesn't mean I'm going to delete anything. Delete selection means I'm going to unselect. So, oops, I selected all. Delete selection. Okay, so if I select the column here, let's say I wanted to turn that column 90 degrees, and I forgot to do it. I could come here in the object, so again, under edit, or under view, I mean object properties. So that's the object properties window over here. I closed the portion manager just because we didn't have enough screen real estate with my monitor up here to see both. And if you go down to rotate degree, so I can change this to 90 degrees if I change it. Boom, there it rotated the column. Okay, or I can rotate it back.
So the
Default is 0, and so it's gonna. It looks like it's putting it in the XZ plane for the web. Y is out of plane, yeah, by default with what we've done here. Of course, it's because I put the frame in the XZ plane, right? right. Now, of course, obviously, given the reasonably good graphics here, you can see what you've got and turn it to what you need, right? Okay. So supports. So everything is member-based. We're going to look at doing a point support. And I'm going to go to a line view because that makes it easier to do things with the point support. I'm also going to go ahead and I'm going to close that for a second, and I'm going to delete my selection so I don't have anything selected here on the screen when I'm working on the next part here. Okay, So I bring up the point support, and what I want to implement is a physical bracing at various locations along the beam. Now I've already worked through the design of this beam, and I know in order to be able to develop plastic moment in this beam for the loading we're going to work, I'm going to need a brace at the midspan. So, and so I'm going to put a brace in the midspan. So where do I want it? Is it braced to the top flange, braced to the bottom flange? Is it braced to the centroid? Where does it go? Okay, so it's a brace that's bracing my frame it's a constraint in the Y direction. So I'm going to scroll down to Y. And I'll say, okay, well, all right, if I leave reference line at 0, it's just going to put it into the reference line, which is the centroidal axis here. If we click on reference line, though, it's a pull-down menu, and I can go top middle. Okay, I will actually want to brace the top flange at the middle. Okay, and then so now, given that, let's pick a point. So you can let it snap to that knee at the corner. Then left click. And it says the next is select the structural object. It doesn't know, do you want this on the column or do you want this on the beam? So I need to pick the beam, or I want to pick the beam here. Okay, it put it in. Now it's a little hard to see with that. If I come back to let me do it the solid view. You can see I've got something that looks very much like a roller there now to the middle of the top flange. That's a constraint. All right. Now I don't have to put these in point by point by point. I can go to multiple support and put in what I need. And so here I'm top middle still what I want. Y is the constraint. I'm going to click on my beam. So here I'm going to have a little trouble. I'm going to go back to my wire view so I can get the reference axis. All right, did I get it? All right. All right, so if I go 2 times 3750, I can put in a brace at the middle and at the very end of the beam. Okay. I think I needed to put that in first. So. Oh gosh knows. I put it in. I'm just not. I think I've probably put in 20 now. Let me see what I've got. So I'm going to select all, and then I'm going to. Okay. Let's see. Yeah. I've got 2 supports there. So I need to delete one. If you end up, oh no, it had it. Okay, it was fine. Okay. Undo. Okay. If I go back to hidden line view or the solid view, you can see I've got those supports at the top flange everywhere. Do you have the same? Hopefully you didn't have as much trouble as I did. All right. So now that's at the top flange. Now in metal building design, a lot of times we have basically many metal building manufacturers will design their frame where every purlin and girt location is assumed to be braced, both flanges, so with flange diagonals from girts and purlins to the inside flange. And then, so they design the frame that way, and then they have a bracing reduction stage where they come back and, okay, what flange diagonals can we pull out and where it doesn't change the design. I'm just going to assume here that I'm going to provide a brace top and bottom at each of the locations here. So I'm going to go back to point support again with multiple supports, 2 at 3750, but bottom middle. Click on my beam, and it's put it in the bottom there now. Okay, we zoom up. So in the line view, you can see the kind of the orangish lines there that's showing the indication for those supports. And I can do the same again for the beam bracing at the knee. We can do a point brace, so I draw there, and bottom middle Y here. He wants to know which object. I pick on the beam. It puts it in. Everybody good? So at this point, for the beam, you should see something like this. Now, I'll use this as an opportunity to say there's this button here where you can get a perspective view that shows you everything. You can get a top view or a front view or an in view. Or you can do an Alt and press your left mouse button down and rotate things around to check what you've got, so we can see that brace we've installed that was hidden by the column. Everybody good? So now I want to do something similar on the column. We're going to put in first a XYZ ZZ constraint. So constrain all displacements and constrain and constrain the twist at the bottom of the column. So if we do that, we can click on that point there at the bottom of the column. You can see it oops, I didn't want that. Need to change this to reference axis because I want my pin support at the base to be a centroidal support. So, all right, so I got that there now. So if we zoom up on that, we can see kind of a graphic that looks, oh, why did it change the size there? Graphic that looks a bit like a pin. Okay. All right, so I'll go back to perspective view. And now we need several other supports. This column is going to need bracing basically at 1/4 of it of its height out of plane on each of the flanges. So we're going to go back to a Y support on the column, and so I need.
So what is this bracing for the column?
This is the out of plane bracing for the column. 3 times, I think.
Is it for the flange buckling or something, or is it for the overall?
It's basically for out of plane bracing on the frame.
Oh, out of plane. Okay.
Out of plane. Yeah, we've been talking about kind of an in-plane analysis, and now I'm jumping to but it's a structure, so we have to actually support it out of plane, right? And then we'll look at, we did a planar analysis, but we can look at the out of plane buckling here in a bit.
But then you need to know how many out of plane bases you need to provide so that
We
you
do.
can overcome into each.
That's right. So I've already looked at the design of this column, and it basically I need 4 braces out of plane to get it close to working.
One at midpoint will not be sufficient.
Right. It won't support the load that I'm going to try to put on it. So if we again set top middle on the column, click on the column, and so if I spin this around, we'll see. Yeah, you can see I just got my supports there on the column on the top middle, and if I do bottom middle and click on the column, I get the support of the inside flange. Now, some of you may be thinking, why didn't I just restrain the rotation and restrain the out of plane displacement rather than doing top and bottom displacement constraints? Either is fine. But if you constrain the rotations, it's a little bit clearer when you show it graphically. Clearly, I'm preventing twist and preventing out-of-plane displacement by these braces that I put at the flange levels here, right, on my column and on my beam. With the column? No, actually, no. So it has the smarts, so to where if I told it to use 4 elements, and I say, oh, but I want some other boundary conditions, it's going to say, oh, okay, so I'm going to have to use some more.
Irrespective of whether it's a node or not.
Correct.
So that's good because your structural stability doesn't dictate the finite element efficiency.
Correct. And generally,
It's the other way.
as a rule, I think they have heuristics where if you leave it on automatic, they automatically put in a mesh that usually works pretty good, but then you can control it manually. All right, now if you think about what we've got here, we should have kind of the supports we would need. It kind of represents a physical structure. Except I've forgotten at this point that, oh, I better support the right-hand end of the beam in the plane of the structure. And so I need another point support. Now I've already put in out-of-plane braces, top flange, bottom flange at that end. And so I need basically a XZ support. There it is, at reference line and here at the end. And I'm going to change back to line view to just make sure I click on the reference axis. All right. So now I put in an extra basically for a planar analysis. I'm going to go back to the hidden line view and I'll do a front view. And so now so a lot of graphics going on here. And I think part of it, usually I think I've got something with my video driver. Hopefully yours looks a little bit more clear. I've got basically a pin support at the base that's also restraining twist. We've got these supports, out-of-plane support of each flange on the column until I get to the top. Now out-of-plane support on the beam at each flange. And we've got a pin support in the plane at the right-hand end. So that correct, at the right-hand end. So if we go back to what we did with the in-plane analysis here, so we basically want to mimic this in-plane problem that we studied earlier, right? But then, but it's actually a physical structure, so I have to provide supports out of plane. So I've already designed that for that and put those in.
Is there a way to extract this as a text somewhere, like a summary of supports or something, because it might be very difficult to...
There is. You can generate a report. Okay, so now what else do we need? Well, we need loadings. So I think we're essentially at, I think it's your step, your 24 say, we've now defined all the support boundary conditions. Let's apply distributed load. Okay, so let's do that. And so for that's the loads is a separate main menu. We can go to line load. That's a member line loading. So that's this button under loads. So if we click on that, in this case our beam has a load of minus 35 kilonewtons per meter, uniform, so both ends. And I'm going to place the load at the top middle of the beam. So top flange loading. And so I need to click on the reference axis of my beam. It puts the loading in. All right, so that's the distributed load on the beam. We also need the concentrated load on the column. So this point load is our concentrated load. You're under the loads menu. We click on that. The column load that I'm going to use for this example is a downward load of minus 770 kilonewtons. And again, I'm going to place it at the top of the beam, so top middle, and I'm going to click on the joint there between the beam and the column. It says select the structural object. I have to tell it, do I want to apply that to the beam or to the column? To the beam. Okay, so it's just put in the 770 there on the beam. Now if we want to check any of these things out, for example, if we wanted to check that loading, we can click on it and say, oh, so that, oh yeah, 770. I could edit that in the object properties menu if I want, as well as change other aspects of that loading if I didn't get it quite what I wanted. So I'll delete the selection and take the selection out. And always, it's probably good to have done a save as well before now. So let's save our model back to.
How do you display the load?
So displaying the load.
Yeah, like that.
Yeah, so it's not coming up on yours. If your load isn't showing, you can come down here to the bottom right and hover, and there should be a button in here that's load. That should make the load visible. Okay, okay. All right, so we still need to specify some details about the connectivity at the knee joint of the frame. And so Balint's going to kind of go more in terms of a detailed explanation of how this actually works next week. Here I'm going to show you how we set it up and use it right now. And so first thing I'm going to need to do is to basically insert. It's called a frame corner wizard. In order to put in a frame corner, we're going to need to bring up our. So I'm going to go back and bring up the portion manager for the beam, and I'm going to go to a line view. And what I need to do is to select the members that are coming into the joint where I want to put in this special modeling of the joint. So I've selected the two members there. And now if we go to custom portions up here at the top, and if you scroll over, you hover on the 1, 2, 3, 4, the fifth button, it's new portion. If you click on new portion, let's just call that knee. Okay, so I've now got a portion of the structure, so I can define any structure we've got. We can say, oh, those are my girders, those are my columns, that's my story. You can basically split up your structure into various portions to manage it for a large system. Once I've done this now, we're going to go back to structural members. And so the frame corner wizard is this button right here under structural members. So I need to have defined that portion that corresponds to those corners. If I bring up the corner wizard, I want to turn it on. Let's see here. What am I doing? Let's try. Let me highlight the knee there and turn it on. Okay. All right. So everybody have that up? So I clicked on this on button for frame corner on. So I need to click on check knee down here at the bottom in the control panel window. And this is a little bit quirky, but I have to also pick on the name of that portion where I want to install this modeling of the knee. So you should have it looking like that, where you've got the name of that portion highlighted. And once you've done that, the sort of type of joint detail that I want to insert, right now it's got this default, which is more of a traditional modeling, where there's no definition of how the warping and the beam and the warping and the in the column and the other degrees of freedom there relate. What I want to do is to model what we might typically have of a frame like this, where we have continuity plates and a definition of a column panel zone in this way. So I want to use that particular model. And so I'm going to apply, and then I'm ready to close. And now you can see that I've got a little yellow box there at the corner. That's telling me I've properly implemented my my model in Consteel that represents how the continuity, including the warping, works at that particular joint. If we come back to our hidden line view, you can see, okay, there's the columns, and then that yellow, the yellow area there, or orange area, is where we've got the panel zone. So we're almost ready to run our analysis of our frame now. So let's set up just a couple of other things, then take a break. Then we'll look at running and expecting some analyses results, and then looking at how that relates to the design calculations. And so for analysis, we want to click on the analysis main button in the second level here. And so under this, the first thing we want to look at is analysis parameters. So it's the second button under analysis here. So if we click on analysis parameters, the specific parameters I want us to focus on here, we're going to do an elastic analysis. First order elastic is by default. We're also going to do a second order elastic analysis. We're going to do a buckling analysis, and we're going to do a buckling sensitivity analysis. So kind of look very tersely at what some of those mean today, and then we'll go into more detail later in the course. Kind of the mantra with this is we kind of set up talking about P small delta, so we're going to look at P small delta, but then, okay, we also defined a frame. All right, yeah, if we design this frame, oh yeah, we have to handle out of plane lateral torsional buckling and all also. And so kind of bringing that aspect in. We'll talk about doing the checks by AISC and by the Indian standard. Okay, so I've got all those selected. So we're now, I can hit apply, or we can go ahead and hit calculation, and we're gonna have some results to look at.